Good day, viewers. Welcome to this class. Today we'll be looking at modern physics. Modern physics, where we'll be talking about aspects of physics such as quantum physics. We'll be talking about photoelectric effect. We'll be talking about the atomic structure of matter. And we'll be talking about nuclear physics and radioactivity. So let's talk about what modern physics is. So modern physics emerged in the early 20th century, and it wants to explain the phenomena that classical physics could not do. So there are some aspects, there are some properties of matter that classical physics could not explain, and we explain that using what? Modern physics. And so some of those things that classical physics could not explain, as the behavior of small particles. So small particles like atoms, your electrons, your photons, how they behave, your classical physics could not explain it. And this led to what we call the dual nature of matter as well and light, where we say that what matter can exist as both a wave and also a particle. We're still going to talk about the dual particle of matter as time goes on. So this topic also explains what nuclear physics, where we're going to talk about Henry Becquerel's discovery and how he did some work on nuclear physics or radioactivity, and how Marie and Marie Curie also did their work on radioactivity, to the point that even Marie Curie earned a Nobel Prize for the work that she did on radioactivity. So moving on from there, this aspect also has helped us to bring about certain innovations, such as your quantum computers, which are no longer using your 0, 1 and zeros in computing. They have higher computing capabilities. So that is what we're studying under modern physics. So the first aspect of this I will be talking about is quantum physics. Quantum physics. So what is quantum physics? Quantum physics is the study of energy and matter at atomic and subatomic levels. So what do we mean? So we're talking about how, remember that we said earlier that physics is the study of matter in relation to energy. So the same thing with quantum physics, also studying matter in relation to energy, but it's not studying matter as a whole. Instead, it is studying matter at its atomic and subatomic levels. So it is studying matter as an atom and the component of that atom. For example, if I have an atom of hydrogen, instead of that atom of hydrogen, I have your protons, I have your neutrons, and I have the electrons. So under quantum physics, we are studying the atom as a whole, which is hydrogen, and we're also studying the properties of the component of that atom. So this aspect of physics was introduced by Max Planck, and he did that in 1900. And under this topic, we're going to be making use of a particular constant we call the Planck constant, and we always denote that Planck constant with H, and it has a value of 6.63 times 10 raised to the power minus 34 joules per joule second. So we have this is 6.63 times 10 raised to the power minus 34 joules seconds, and we call it the Planck's constant, named after Max Planck. So Max Planck did some work on this, and he said that energy is not continuous, but it comes in discrete packets, and this packet or these forms in which energy is found according to Max Planck is what we call quanta. So, and he brought about this formula that says that the energy is equal to, or energy has a direct relationship with the frequency. And when we now introduce a constant, we now have energy to be equal to Max Planck's constant times the frequency. So moving on from there. So this energy, like we said before, they are in the form of quanta, or in form of quantum for singular. So then F here is talking about the frequency of the radiation, and this frequency of the radiation there's also a fundamental frequency part of it we're going to talk about when we start the calculations on this. So what are the key ideas of quantum physics? Now, one of the key ideas of quantum physics is the wave-particle duality. What is the wave-particle duality? It's simply saying that wave that wave generally can exist as both a particle and can also exist as or matter generally can exist as both a particle and can also exist as a wave. So we can have matter existing as a wave in the form of diffraction of wave. So matter, which is what our case study here, can what exist in terms of diffraction, in terms of what reflection, in terms of refraction of waves. So that is what wave particle duality is talking about the ability of matter to exist as both a particle and can also exist as a wave. Then another key idea that we have under this quantum physics is the Broglie hypothesis, where it said that what particles like electrons have wavelengths. So that's why we came about the values for what the speed of electrons, and we also get what we call the wavelength of electrons. So he said that what particles generally, and we know that what matter is made up of what particles. Inside your matter, you have molecules, we have atoms, and we even have radicals or ions. And these particles can be further splitted into subatomic levels or even atomic levels. At the atomic levels, you further split it to form what protons, neutrons, and electrons. And according to de Broglie, he said that what these electrons have what wavelengths. So, and he said that what the wavelength is equal to the mass and the velocity times what Planck's constant, which is what we have what our wavelength is equal to what the mass, the velocity times Planck's constant. So this is what de Broglie's hypothesis, and he did this hypothesis 24 years after Planck's discovery. Moving on from there, we have that this explains that electron diffraction and quantum mechanics. So what's that de Broglie's hypothesis is just talking about? It's talking about what the diffraction of electrons and what quantum mechanics. So let's talk about the third one, which is what Herzberg uncertainty principle. Herzberg also brought about a principle that we call the what uncertainty principle, and he said that it is impossible to measure both the exact position and the momentum of a body. You cannot measure the exact position and the momentum of a body simultaneously, which means you're either measuring the momentum of a body, or you are measuring the exact position of a body, but you cannot do them together. So that is what we call the uncertainty principle. So according to Herzberg, you have to measure either the change in momentum separately, or you measure the exact position of a body, but you cannot do both happening at the same time. So moving on from there, that takes us to what we call the photoelectric effect. Remember that the first thing that we talked about is what quantum physics. So number two, we're going to talk about what the photoelectric effect. Now, the photoelectric effect is simply saying that there's an emission of electrons from a metal surface whenever there is a light of sufficient frequency shining on it. It's saying that whenever light hits a metal at a particular frequency, so that it exceeds the threshold frequency or the minimum amount of energy that is required for electrons to leave the metal. That would called threshold frequency. So it's saying that whenever light hits a metal, there is an amount of electrons that is given off from the metal, so long as the frequency of the light hitting the metal exceeds the threshold frequency. And this principle is what we call the photoelectric effect. And it is this photoelectric effect that you can see that your solar cells, or what we call your photo cells, the full name is actually photovoltaic cells. So your photovoltaic cells or your solar cells, they use this principle of photoelectric effect to generate electricity, so that when sunlight hits the photo cells by themselves emit electrons, and these electrons are carriers of charges. So these charges that are transmitted to your panels, and from your panels to your storage equipment, and that electricity cannot be used around your houses. That's what using the photoelectric effect. This was discovered by Henrik Hertz. Henrik Hertz is also the person by which we named the unit of frequency, because according to the photoelectric effect, it uses the frequency of the light. So if the frequency of that light hitting the metal exceed the threshold frequency, then there will be emission of electrons. But if it does not exceed the threshold frequency, there will be no emission of electrons. And that was what discovered by Henry Hertz in what 1887. But this was further explained by Albert Einstein in 1905. Albert Einstein did a more pronounced work on what this work of what photoelectric effect that was formally introduced by Henry Hertz. And with that discovery of Albert Einstein, he won the Nobel Prize in what 1921. And that was the first Nobel Prize that what Albert Einstein won, and it was based on what this photoelectric effect. So that brought about Sir Albert Einstein bringing out a formula that says what HF is equals to work function plus half mv squared. So where my H there, we're talking about the energy of the incident photon. So now photons are the forms in which light hits your metals, for which what electrons are now emitted from it. So photons is just like the forms in which what light is what transferred into the what metals. So your W in that word formula is what work function, and we know that our what half mv squared is talking about what the maximum kinetic energy of the ejected electrons. So what are the key features of this? Moving on from there, the key features are: first one, no electrons are emitted if the frequency is what less than threshold frequency, no matter how intense the light is. What is this saying? Like I said before when I was explaining the photoelectric effect, I said that what for electrons to be emitted, that the frequency of that light that is hitting the metal must be higher than the threshold frequency. And what is the threshold frequency? The threshold frequency is the minimum amount of what energy that is what required for electrons to be emitted. So the minimum, so long as the frequency of the light coming exceed the threshold frequency of that particular metal for electrons to be emitted from it, then your photoelectric effect can take place. But so long as your frequency is less than the threshold frequency, there will be no photoelectric effect, irrespective of the intensity of the light. So even if the light is very, very intense, it does not affect the emission of electrons, so long as the frequency of the emission, so long as the frequency of the incidented photon is not higher than the threshold frequency. 2. The intensity affects the number of electrons, not their energy. Now remember we said that what for electrons to be emitted, that what it is the energy that determines what the emission of what electrons. But the number of electrons emitted depends on the intensity. So it requires what the energy for the electrons to be emitted, but the number of electrons that will be emitted depends on what the intensity. So how bright the light is will determine how much electrons will be emitted. But the frequency of the light will determine whether electrons will be emitted at all or not. So number 3, it said what the energy of electrons depends on the frequency of the light. That's what we just said earlier. That what the energy of the electrons is depending on the frequency of the light. That is what is incidented by the photon. So what are the applications of your photoelectric effect? Like I said before, your photoelectric effect is what applied in your solar cells. So your solar cells are also called photocells or photovoltaic cells. So they are also what applied in automatic doors that you do not have to open by yourself. So when you walk close to the door, it opens on its own. They are automatic doors. So they are also applied in light sensors. So they all use what we call the photoelectric effect. Number 3, we're talking about what? The atomic structure. Now, what is an atom? An atom is the smallest indivisible part of an element, according to John Dalton. But this was what was said to be incorrect in the modification of Dalton's atomic theory, because according to what other scientists that worked on this, they said that what atoms can be divided. so long as it is not what a chemical process. So in non-chemical processes, such as a nuclear reaction, atoms can be splitted, atoms can be broken down, atoms can be divided. In fact, atoms can disintegrate into smaller atoms in what? Nuclear fission. So atoms can be splitted into electrons, protons, and neutrons. While your protons and your neutrons are present in the nucleus, the electron revolves around the nucleus, such that I have something like this. So if this is the nucleus, I have electrons in shells or orbits. So looking at this, in this particular atom here, I have 11 electrons, and I have what? My protons and my neutrons within the nucleus. So this center here is called the nucleus. And this here is electron. So inside the nucleus, this is where I have my protons plus neutrons. So your proton number, the number of protons present in an atom is always equal to the numbers of what? Electrons present in the atom, provided that that element or that atom is not in excited state. So in the ground state, your proton is always equal to your electrons. So what are the key models of what? Your atomic structure. Now the first model we're going to talk about is Thomson's model. Thomson's model is now obsolete. What do we mean by obsolete? Is no longer in use because of his what? Outdated function. Now, according to Sir Thomson, he said, J.J. Thomson said that atom is a sphere of positive charge with embedded electrons. So this particular model is now what? Obsolete. It is no longer in use, as what? Modifications have been what? Introduced. Moving on from there, we have the second model, which is what? Rutherford's model. Rutherford's model was introduced in 1911, and he discovered that what? The nucleus via what? A gold foil. So he used a gold foil in his experiment and discovered that what? The nucleus is what? Present in what? In the gold foil. So it was one that discovered what to call what? The nucleus. So the nucleus in that diagram was discovered by what? Rutherford. And most of the atom is empty space, according to him, because he did not know that what they were what? Electrons revolving in those what? Orbit. So he discovered that inside that atom that there is what? A nucleus. And that is where what? Rutherford stopped. Then Boyce in 1913, after the discovery of Rutherford, Boyce went for that Nell Boyce. So Nell Boyce went for that to discover that what? That electrons move in quantized orbit, saying that what? These particular what? Electrons are moving in different orbits, and these orbits are in quanta, meaning that what? The level of energy of this first what? Orbiter here is different from the level of energy of the second orbiter, and it's different from the third what? Orbiter. So he's saying what? Electrons are moving around these orbits or orbiters here, what? Based on the amount of energy that is what? Present in them. And for you to remove an electron here, the amount of energy is different from what? The amount of energy that will be required to remove an electron here. So you say that what? Electrons move in quantized orbits, and they absorb or emit photons when jumping between energy levels. So what he's saying is that for an electron to remove from here, or for an electron to move from here down to this next energy level, that what? There must be what? An emission of what? Photons. So that is what Boyce discovered. So it was Boyce that discovered what we call shells or orbitals in what? In the particles of an atom. Moving on from there, that takes us to the modern view, what we call what? Quantum mechanical model. So what is the quantum mechanical model? First, we know that what? Electrons exist in orbitals, according to what Boyce have said, and these are regions of what? Probability. So the orbitals are what? The regions of probability. And we also know that what? Energy level explain atomic spectra, where bright lines in emission or absorption spectra. So what we are saying here is that what there are energy levels. Despite the fact that what electrons are in orbitals, but they are still energy levels. So moving on from there, we have the fourth part or the fourth aspect of what this topic is what we call nuclear physics. Nuclear physics. So this is an aspect of nuclear physics studies the what? The nucleus and its forces. So we're talking about what you have inside the nucleus. What are the forces that held that nucleus together? What is holding that nucleus in place? So what are the properties of the nucleus? First, the nucleus contains the protons, which is a positive charge particle, and contains the what? The neutrons, which are generally neutral. And then I said earlier that what? Inside this nucleus that we have what? The protons and the what? Neutrons. And these protons and neutrons are what make up what we call the mass number of an element. So the mass number of an element is determined by the number of protons and the numbers of neutrons. So when you add the proton to the neutron, what you are going to get is what? Mass number. I will represent it with what? A. So if you see an element when you write something like this, it means that I'm having the atomic number and I'm having what? The mass number. So A here is representing the what? Mass number, and Z here is representing the atomic number. And the atomic number of an element is determined by the numbers of protons present in the element. So the number of protons present in an element will determine what? The atomic number. And remember I said something earlier that what? In an atom, that so long as that atom is not in a excited state, that means it is not an ion or it is not a radical, as in the case of group of atoms, then it means that your electron number must be equal to what? Your proton number in the ground state of an element or an atom. Moving on from there, we have the nuclear forces. What are the nuclear forces? These are strong, they are strong nuclear forces that hold nucleons together. Remember that we said what? These protons and neutrons are present inside the nucleus. So the nucleus is one half in it. So the protons and the neutrons are called nucleons. So these two together are called what? Nucleons. They are present inside the nucleus and they are what? Held together by strong nuclear force. And this nuclear force is a lot greater than the electrostatic repulsion. What is electrostatic repulsion? Is the force of attraction that what? The force of repulsion that is existing between particles of what? Like charges from what? Either the positive and the positive or the negative and the negative. So that takes us what we call what? The binding energy. So the binding energy that holds the nucleus together is called, the energy that holds the nucleus together is called the binding energy. It's a force that what combines all the particles of the what? Nucleus together. And this was brought about by what? A formula that was stated by what? Albert Einstein, where he said that what? The energy is equal to what? Change in mc squared. So this formula was what? Introduced by Albert Einstein, where your change in m is talking about what? Mass defect. Moving on from there, so that takes us to what we call nuclear reaction. Nuclear reaction. So what are nuclear reaction? We have two types of nuclear reaction. We have what is called nuclear fission and nuclear fusion. Nuclear fission is the splitting of a giant molecule into simpler molecules and the release of energy. So the splitting of heavy nucleus, e.g. uranium 235, to release huge energy is called nuclear fission. And this is used in nuclear power plants and atomic bombs. So if you drop an atomic bomb, what actually happens is that when the atomic bomb will lose some energy. It is that energy that causes the explosion. So likewise, in your nuclear power plant, when you drop your particles into that nuclear power plant will split those particles. They will be broken down and they will usually release of energy. It is that energy that is what released that is now what transmitted toward the generation of electricity. So that is what we call nuclear fusion. What is nuclear fusion? This is a combination of light nuclei So when you combine light nuclei together, when you combine smaller nuclei together, to form a giant molecule, it is called what? Nuclear fusion. This occurs in the sun. So how does your sun get its light? It is via nuclear fusion. There is constant what? Combination of particles of what? The sun. Hence it is what? Constantly burning bright. So, and this can be found in what? Combination of helium, hydrogen, what? Isotopes to form what? Helium. So this occurs in the sun and hydrogen bombs. There's another type of bomb that we call what? Hydrogen bomb. So, and it was more energy per unit mass than what? Fission. So what do we mean? In nuclear fusion, there is what? More energy generated compared to what? Nuclear fission. Moving on from there, that takes us to the fifth aspect, which is radioactivity. Now, radioactivity is just like a subtopic under nuclear physics. So, and radioactivity is just the spontaneous emission of radiation from unstable atom or from unstable nuclei. And this was discovered by Henry Becquerel. Henry Becquerel is a French scientist, and what? He went further to what? First discovered this when he was what? Observing what we call pitch blend. There was a blend of uranium with other particles, impurities, and when he was observing it, that particles, that combination of what impurities with that uranium was what we call what? Pitch blend. And when he observed it, he discovered that what? There was emission of what? Radiation, and hence he was what? Given the title of the father of radioactivity, because he was the first person to actually do work on radioactivity that was what? Recorded. But other people that also do work in radioactivity were chemists such as Marie and Pierre Curie, who what? So the point that what? Even Marie Curie won the Nobel Prize for this particular work that she did on radioactivity. So what are the types of radiation? We have the alpha radiation, we have the beta radiation, and we have the gamma rays. Moving on. So the alpha particle or the alpha radiation is what? Made up of helium particles. So we have what? Helium 4, 2. So we have helium 4, 2. So this here is what is emitted from what? An alpha particle. So if, for example, your uranium emits this, emits that reduced by what? Atomic number of 2, and it has reduced by mass number of 4. So, and it is what? It is a weak emission or a weak radiation where only small particles are what? Emitted, and it can easily be stopped by what? Paper. So this type of radiation can be stopped by what? Paper. So moving on, we have the beta radiation or the beta particles. These are high-speed electrons or positron, and it is moderately what? Penetrating. It has what? High penetrating power than the what? Alpha radiation, and it can only be stopped or with something a little bit higher than a piece of paper, like what? Your aluminum foil. So you can use your aluminum foil to stop your what? Beta radiation or your beta particles. So the next one is the gamma rays. Now your gamma rays are what? Electromagnetic in nature, from what? Electromagnetic wave. So they are examples of electromagnetic wave, and they are what? Very penetrating, and they can only be stopped by what? A thick lead block or what? A thick concrete. So the amount of what? Radiation that is present in it is what determines the type of what? Radiation. What is emitted from it, from a particular particles, is what determines the type of radiation. So that brought us to what we call the radioactive decay law, or where we use what? Decay constant, where we say that what? N is equal to what? N naught exponential minus alpha t. So here minus lambda t. So this is just what? A formula that we use for calculating the amount of what? Substance that is left after what? A particular decay or after a certain half-life. Moving on from there. So let's talk about half-life. So half-life is the time it takes a particular radioactive element to decay up to half of its entire quantity. So if, for example, I have a substance, let's say I have 20 kilograms of uranium, and the half-life is 10 seconds, for example, it means every 10 seconds, this 20 kg of uranium is going to divide itself into two. So the first 10 seconds, what I'll be having left will be 10 kg. The next 10 seconds, what I'll be having left will become what? 5 kg. The next 10 seconds, what I'll be having is what? 2.5 kg. So half-life is just talking about what? The time it takes what a radioactive element to decay up to half of its original size or quantity. And you can calculate it using the formula that says what? The T half, which is half-life, is equals to 0.693 over lambda. Moving on from there, so that is the applications of radioactivity. Now, one of the applications of radioactivity is in the cure of cancer. They use it for what? Chemotherapy as a form of what? Curing different types of cancer. Another thing that we use it for is for what? Generation of energy. We have what we call nuclear power plant that is used what? For what? Generating energy, electrical energy. And we also use it for what? Carbon dating. We use it for carbon dating. Carbon dating is just what? A system where you can find the age of an organism or a substance by what? Using radioactivity to find out how long that substance has what? Existed. So we use it for checking the forces of what? Organisms that have existed on the earth even before arrival. And that is what? Carbon dating. We also use them for smoke detectors. So in your smoke detectors, what you have there are radioactive materials. So we've come to the end of today's class. In conclusion, radioactivity or modern physics bridges the what? The microscopic world of atoms with the macroscopic world. So you are bridging the microscopic with the macroscopic, and it explains the phenomena such as why the sun shines and how semiconductors work. So how does a semiconductor work is under what? This topic, and how nuclear energy is harnessed, how you can use your what? Nuclear energy to generate electricity. So from the quantum revolution to radioactivity, it is the foundation of advanced technology today. So this topic or quantum physics is just talking about what? Advanced technology and how you can harness it in making what? The world a better place. So we've come to the end of today's class. Don't forget to go to our channel for more videos just like this, and also we've done a question and answering session on this topic. Don't forget to go to the channel to check it out.
Hi, I'm sure you enjoyed the content you just watched. To see more episodes as that, preparing you for your oncoming exams, smash the subscribe button on this channel right now and visit the playlist that we've made for you, covering over 50 type of different exams, including JAMB, WAEC, Cacao,